G'day guys. In this video I thought that I would take you through a hacky snake clone that I put together in Python and PyGame. I do want to say before we start that I'm certainly not a Python guy myself. My bread and butter is usually C#, which is quite a different beast. So if you are a Python guy, you may cry at what's about to follow, but if you are kind of getting started with Python or getting started with programming in general, I thought this might be hopefully useful to somebody. So yeah, without further ado, let's get into it. Before I actually open up or run through any code, I wanted to actually show you guys the game, just since it's often easier to understand the code that you see if you have an idea about what it's supposed to do or what it's trying to do beforehand. So let's take a look at the game. Alrighty, let me just pause it for a second. So we've basically got a grid. This white block here is the snake. This little green block here is the apple that the snake is supposed to eat. The controls are basically press left on your keyboard to go left. Can probably unpause it to show you guys this. Press up to go up. Press left to go left. Press down to go down. Press right to go right. If you move over the apple, you eat it, and the apple regenerates somewhere else randomly. The snake gets a little bit bigger. Let me just try to eat a few more just to grow a little. The reason why it's kind of grid-like and kind of choppy is I don't know about you guys, but my first experience playing Snake was around 1999 or 2000 on an old Nokia 5210, and that phone. Oh, what's happened here? Oh, it's regenerated in the same spot. Yeah, that phone didn't even have color, so I wanted to kind of recreate that feel if I could, and that's the choppiness. Anyway, as for controls and behavior, if part of the snake collides with itself, like what just happened there, you die and you regenerate. If you hit any of the walls, you also die and regenerate. So that's pretty much the controls and the expected behavior of the game. So with that, let's actually take a look at the code. So to start off with, we've got our imports up at the top. The first one is PyGame. So this is really the only package that you kind of need to run this. So if you want to use a Python virtual environment, you can. If you don't, I'm not going to say you have to. So that's just a pip install PyGame. These modules are classes that are actually in the directory, so you won't need to install those. Here we're setting up basically the different colors that we're going to be using. So we use white for the snake, black for the screen, red for the grid, and green for the apple. So these are all RGB values, where the first value here is the value for red, from 0 to 255. Second is for green, and the third is for blue. We initialize the game, and we set the screen size to 700 pixels wide and 500 pixels high. Here we basically create a surface. So we're using the PyGame SDK to create a surface with the dimensions that we set up earlier. And this screen is the surface that we're going to be using for drawing all of the stuff that happens in the game. We set the caption. If you remember, snake was basically the title of the window that showed up earlier. We store a reference to the clock, basically so that we can control the FPS, but it's more than just the FPS. It's also, you could say, the frequency of our game loop. We've got a few different components. So there are kind of three things that make up the game. We've got our grid, we've got our snake, and we've got our apple. And we'll go through each of these classes shortly, but I want to go through the main file first. So we're setting up the grid to be 50 pixels by 50 pixels in terms of like each square in the grid. We're passing it the screen that we created earlier, so that's the surface that we're going to be drawing on, and we're passing in the red color. That's going to be the color of the lines. And similarly for the snake, we want each block or each section of the snake to be 50 pixels by 50 pixels, so to occupy exactly one square in the grid. We pass in the surface that we're going to draw on, and we want the snake to be white. With the apple, we want it to be 25 by 25, slightly smaller. We also pass in the size of the grid though, because we use that value to kind of position the apple in the center. And similarly, we pass in the screen for us to draw the apple on, and we pass in the color. I do have some background music, but I've just temporarily set the volume to 0 so that you guys can actually hear me. And then we've got a couple of control loops. So the first loop is to basically keep the game running. So this is our game loop that we're about to enter. If you look at most games, except perhaps those that are written in more of a high level language where there's more magic that the framework is taking care of. Most games will have some sort of a game loop where the code will be checking for inputs and checking for events, moving things around, performing game mechanics like jumping, applying gravity, moving the enemies, and all that sort of thing, doing collision detection, physics, and lighting, and yada yada yada, and then updating the screen. So, and that needs to happen continuously because within a second things can move, things can change. You can push a button. So that game loop needs to be constantly running and checking for all of those things and updating the game world and eventually updating the screen. So you'll usually have some kind of a Boolean variable, a true-false variable that basically says the game is still running. And that's basically what this loop is doing here. We also have another variable to control whether or not the game is paused. So as we saw earlier, you may want to pause the game, and when you do that, the loop kind of still needs to be running because you don't want the game to quit or the game to exit, but you just want certain, you could say most, aspects of the game to kind of stop. So nothing's moving anymore, you probably want to stop the background music, and so on and so on. So that's what that is for. Inside our game loop, we kind of do, say, two main things. We've got our event handling, and then we've got our update. So with our event handling, there's kind of two types of events that we want to handle. The events themselves are basically coming from PyGame. So PyGame has its own event system pretty much. So we can just ask PyGame, hey, tell me the events that have happened now. And the two types of events that we want to handle are key downs and if the program has quit, so that we can kind of exit gracefully. So if the user clicks that red X button in the window to actually close the window, or they hit Alt F4 or Command Q or whatever. In other words, if the operating system is sending us an exit command, we want to set the running loop to false. When the loop reevaluates, it will evaluate as false, and then it will continue running, which is this PyGame.quit. So that would let PyGame exit gracefully, close up any resources that the game is using, and so on. But let's look at the more interesting stuff. The key handling. When somebody presses a key, as we saw, if you press the left key, we want to move the snake left. If you press the right key, we want to move the snake right, and so on. So what we're basically doing is we're checking the key property of the event, and depending on the key property of the event, we're setting the direction on the snake. So we'll look at what that method does when we look at the snake class. I've got a couple of little cheat codes here. So if you want to move the apple, you can press down the A key. That may come in handy depending on how much of a cheater you want to be. There's also the P key. So when you press P, that pauses the screen. And when the screen is paused, we perform a little trick here where we basically set the paused value to the opposite of whatever it is now. So we perform a not operation on it. So what that means is if running is currently true and we run this line, it will set it to not true, in other words, false. And if running is now currently false, it will set it to not false, in other words, set it to true. So that's a cool little thing that you can do with booleans. If the game has just been paused, we want to pause the music and then basically continue. Probably don't need that continue there, but anyway, otherwise, if the game is not paused, we want to resume playing the music. So that's our event handling. Now, if the game is not paused, so if the game is paused, we don't really need to move anything, we don't really need to draw anything because nothing is happening. So that's why we've got this extra condition here. But if the game is not paused, then we need to actually perform some calculations, move things, update the screen, and do regular game stuff. So first things first is we want to move the snake. We saw earlier that we set the direction of the snake depending on the key that got pressed. Now that we've set the direction, when the game is running, we want to move it. And then we've got a few little things that we need to check. So if the snake is out of bounds, in other words, if it's to the left of the left side of the window, above the top of the window, past the right end of the window, or past the bottom end of the window, it's out of bounds, and the snake should die, and the game should kind of restart. Otherwise, if the snake is eating itself, so if the front of the snake collides with any other part of the snake, you also die, and the game should restart. If the snake collides with the apple, so the snake is eating the apple, then we want to kind of reset the apple. The apple should disappear from where it is now and reappear somewhere else, and the snake should eat the apple, so the snake should grow by 1 unit. So that's the game logic. Next, we've got a bit of drawing logic. So we want to fill the screen with black, that's the background color. We want to draw the grid, draw the snake, draw the apple based on the current positions of the snake and the apple. So this is just drawing logic. It shouldn't be performing any calculations about, where the grid is or where the snake is or where the apple is. It's just for drawing. And then we want to perform a flip on the display. This line, on the surface of it, which is actually a pun, but you may or may not get that pun. On the surface of it, this line might look a little confusing, like what the hell are you flipping? But if you've ever worked with 2D games before, the way that the surface actually works is when we draw something on a surface, so let's say, for example, we draw the grid, the changes made to that surface aren't immediately visible. And there's good reason for that. If the changes that we make to a surface, which is basically screen, we declared screen up here and we pass screen into the grid, into the snake, into the apple. So they're all using the same surface. When we make a change to a surface, the change isn't immediately visible. And the reason for that is, if you can imagine, we draw the grid, um, and let's say, for example, this is a little bit of a slower machine. What you might actually see the grid being drawn. So the lines going down the screen and the lines going across the screen. You might see each block that makes up the snake. So one yellow square, one white square, another white square, another white square, being drawn in real time. And of course, that's really jarring for the user to see all that stuff. Okay, granted, nowadays computers are pretty fast, so they probably wouldn't see each line being drawn like this, but there might still be a bit of a flicker. So the surface isn't visible until we flip it. So all of the drawing operations take place on an invisible surface, and then when we flip it, the assumption is that all of the basically the screen is ready to be shown. The new frame, if you want to think of frames in a game, the new frame is ready to be shown. So that's what happens when you flip the surface. Here we're basically telling the game to sleep for a little while. So here we want 1 update per second. So what you'll notice is this loop log that I've got running down here, which basically fires at every cycle of the loop. That loop only gets logged once every second. So it corresponds to the ticks in the game. So this isn't just controlling like screen updates. It's actually controlling the program flow. And that's kind of good, because when the game is paused, you don't want the loop to be smashing your CPU. You kind of want, while the game is paused, continue this flow of, sleep for nearly a second and then run again. So that's kind of the main logic of the application or of the game. You'll notice though we do have quite a few files on the left here, so we can take a look at those. Probably a good place to start might be the grid. So inside the grid, we're importing PyGame. Unsurprisingly, almost all of our main components are going to be using some aspect of PyGame, particularly for drawing. And we're actually creating a class for the grid, and we'll use basically a class for each component. I'm not going to get into the theory of object-oriented programming here, but you can just think of a class as a reusable component. So up the top here, we're creating a new instance of a grid, a new instance of a snake, a new instance of an apple. If we wanted to have 10 apples on the screen, we could just run this 10 times, and we would get 10 different copies, 10 different instances of whatever apple contains. So I think that's enough background on classes for this video. If you have worked with classes before, this is pretty much the Python equivalent of a constructor. So it's the underscore init underscore function, which takes in at least a self parameter. So self kind of corresponds to this, if you've ever used JavaScript or Java or any other object-oriented language. If you've never used any of those before, that's fine. Self refers to the current instance or the current copy of whatever the class is. So the current instance of the grid. Now, for all of our classes, we actually only have one instance, so you don't really need to pay too much attention to that concept. But that's basically what self is. And when you're working with classes, you generally do need to use self quite a lot. The grid will have properties. The grid will have bits of information about it, and that information is stored in self. So we have some other parameters here. We're passing in the size, surface, and color, which correspond to these three here: size, surface, and color. Self doesn't get passed in. So if you look at these and say, hey, there's four parameters here, but only 3 arguments, Self is kind of, an invisible an invisible parameter. You can really tell that Python is quite embracing the functional programming concepts, because as you can see here in draw, like self is repeated again. Everything is provided as an argument. As an argument to your functions. Anyway, so we accept the size, surface, and color, and we assign those to the self so that we can refer to them later. And whenever we want to draw the grid, we basically want to get the total height and total width of the surface, which we defined here. We set the current y and x to the size that we passed in, so 50 and 50. And we want to draw vertical lines and horizontal lines in increments of 50. So that's basically what these two loops do. So we draw the horizontal lines first, and we draw an anti-alias line, which basically just means that it shouldn't be a blurry line. That's what AA stands for. And we just go through vertically and then horizontally to draw a grid. Next, perhaps let's look at the basic building blocks of the snake and the apple. So the basic building blocks that we're working with are coordinates. So coordinates are another class, and we've got another init function which takes in a self that we don't provide it. This just refers to the current coordinate, and we pass in x and y, and we just assign them, and that's it. Building on top of a coordinate, we also have a square. So this is a very retro sort of a game. So everything is pretty much a square. We don't have any 3D stuff going on, no weird triangles or other polygons. Everything's a nice and simple square. So square builds on top of a coordinate. So we're importing coordinate, and what we're actually doing here is we're saying that the square inherits from coordinate. So this is basically inheritance in Python. Even though inheritance is an object-oriented principle, it still somehow looks like a function. It looks like the type is being passed in as a parameter to square. Looks cool. And all we're really saying here is coordinate is the parent or the foundation of square. So square gets everything the coordinate has plus whatever square adds. So we've still got an init function. So this is what's initializing the square, what's setting up the square. It's the constructor for square. And the first thing that we do is we call super. So super here refers to superclass. In other words, the parent class, which is the coordinate. And it's calling init on the coordinate and passing in x and y. So those basically correspond to this init function here in coordinate, passing in x and y. And in addition to what's in coordinate, a square also has a size. So the length and the height are both equal, hence it's why it's a square. And we're just storing the size in self. So we've got coordinates, we've got squares, then we have stuff that are based on square. So let's look at apple. So again, we've got our imports, and we're inheriting from square. So apple is a square, rather small square, but it's still a square. So it has x, y, and size. We've got an init function, we've got a constructor, which takes in a size, a grid size, a surface, and a color. And if we go back to main, we can see that. So when we create an apple, we've got a size, a grid size, a surface, and a color. So the size is 25 pixels. We want the apple to be a little smaller than the actual square, just so that it doesn't look weird. What we do then is we say, okay, I need to set up the square. I need to set up the parent class. So I pass in x of 0, y of 0, and a size of whatever got passed in, which in our case is 25. We then set the grid size, surface, and color, and we call reset. So we've put the kind of initialization or position calculation logic inside reset, because after you eat an apple, we need to repeat it. So that's why we put it in here instead of having all of it inside the init function. For max y, we basically want to, for max x, we basically want to take the width of the surface, so 700 pixels, and minus the width of the apple, so that you can't draw the apple already off the screen. Same thing for max y, but we do it vertically. Now we want to randomly put this apple somewhere. We want it to be put in a random position somewhere on the screen. But beforehand, we calculate this buffer, and we calculate the buffer because we want the apple to be kind of positioned in the middle of a square inside the grid. We don't want it to be all the way on the left or all the way on the right or all the way on the top or bottom. So we basically say take the grid size, if the grid size is 50, minus the size of the apple, which is 25, so this will evaluate as 25, and we divide that by 2, so we get 12.5. And that way, we want 12.5 pixels basically on each side, 12.5 on the left, 12.5 on the right, top and bottom. Then to calculate the x position of the apple, we basically use the random library in Python to generate a random number, a random integer, a whole number, between 0 and the max x that we calculated earlier. So the entire screen width minus the width of, minus the size of the apple. So we get that random number, and then we want to round it. So, you know, if we got any old random number, we could end up partway, like we could end up overlapping the red line in the grid. And we don't want to overlap that red line. We want to be placed nice and squarely, nice and squarely inside one of those cells. If I run this again, just so that you can see what I'm talking about. Oh, sorry. I'll just pause it again. See how the square is kind of flush in the center? We don't want it on one of these red lines. So that's why we need to do this little bit of extra work. So I might just keep the game running and come back. So we want to round it to the nearest grid size, which we passed in as 50. We want to round it to the nearest 50 so that we can get basically flush inside one of these squares. But it's not enough to be flush. We also want it to be centered, and that's where the buffer comes in. So we add the buffer, and that's what basically gets it nice and centered inside the square. And then when it comes to drawing, it's pretty much almost the same as what we did for the grid, except instead of drawing a line, we're now drawing a rectangle. So that's the apple. And the last thing is the snake. Sorry if you guys are getting tired, but we're nearly done. If you are curious about this utils thing that we used before we get into the snake, this is a little utility class that I created just for the rounding, because this rounding logic is shared between apple and snake. Now, okay, I could have put this rounding logic inside square, because square is also common to both apple and snake. But rounding doesn't really have anything to do with a square, so it makes more sense to put it inside of a completely independent utility class, and that's what this is. So we've got a utils class. Couple of quick calculations here just to make sure that it sort of makes sense. And I've marked it as a static method. So a static method is a method in a class where you don't need a new instance of the class to use it. So let's come back to main. Look at what we're doing here with the apple. or with the snake, we're kind of passing some arguments. This 50, this screen, this white. These are arguments that we pass into snake, and we get back an instance of the snake. And then whenever we want to use the snake, we use the instance of the snake, not the class directly. Whereas under Apple, we just call utils. We don't have to, create a new instance of utils with the brackets. We can just use the name of the class directly. And the reason why we can do that is because it's marked as static. And the reason why it can be static is that it doesn't use any stored information. Like looking at the apple, whenever we reset the apple, we're using things that are part of the apple. We're using the surface, we're using the size. Whereas utils doesn't use any of that stuff. It just uses the parameters. It just uses what's passed to it. That's why it can be made static. Sorry if you guys already knew that, but I wanted to cover it just in case anybody didn't. All right, so I think we're onto the big guns now. We're onto the snake. And the snake is the trickiest part of making snake. So it's another class which inherits from square. We've got our init function, we've got our constructor, we accept size, surface, and color. We call super on the square to initialize the square with x, y, and size. We set up the surface and the color, and then we set up some sounds. So the sound that is going to play when you die, when you eat, when you cancel is for when something is cancelled, when something cannot happen. So let's come back to our game. Let's unpause it. This is basically handling the scenario where you try to navigate in the opposite direction that you're currently traveling. So I'm moving left. If I press the right key, that's basically not supported. Like otherwise the snake would be going backwards on top of itself. So if I press the left key, it basically won't let you do it. And that's what that ugly, horrible sound is. Anyway, then similarly to what we did with the apple, we call reset. So all of the positioning logic is inside this reusable reset function. Because if the snake dies, we need to be able to rerun it. So the stuff that's in your init function, the stuff that's in your constructor, should not really be stuff that you need repeated. If you need to repeat it, you want to pull it out. All right, so let's take a look at what goes on here. We start off with 5 blocks. So we've got 1, 2, 3, 4, 5. We start off traveling in the right direction. We start in the position which is 1 block away from the left-hand side. Now, to be honest, you won't really be able to observe this because the snake has already moved by the time the game starts, or by the time the game is observed. But that's the starting position. Here we use utils again, and we want to, the starting position of the snake basically should be the middle of the screen vertically, but we want to round it to the nearest grid size. So again, we don't want to overlap these red lines. We want it to be flush inside the grid. And then we want to position the blocks. So dealing with the blocks is probably the trickiest part of making snake, since you're dealing with multiple rectangles or multiple squares that need to kind of stay in sync. So the way that we started off is with a new array. We create a square with the starting x and starting y and size. So this will be, you could say, the head of the snake. This is basically recreating an old-fashioned for loop, since in Python the regular for loop is in fact what is considered a for each loop in other languages. So what I basically want is I want to maintain the position in the array or the position in the loop that I'm currently at, and a for each doesn't give you that. So that's why I'm doing it kind of by hand, using a while loop and a counter. So while the current block is less than the length of the snake, I could also use len here with self.blocks. Yeah, you could also do that. I calculate the new position of the next block, which is basically the position of the previous block minus the size. So when the game starts, let's just say, for example, this square here is the head. The x-coordinate of the previous position is going to be the x-coordinate of this position minus the size. So that's how we calculate that. And then we append it. And each block is a square. And then I add 1 to the current block, and the loop will repeat. So that's how we initialize. When it comes to moving, we basically, whenever you press a key, we want to set the direction. But remember, we had this logic around preventing you from moving in the opposite direction. So in other words, if you're currently moving left and the user tries to go right, we play that horrible sound and we return. So we exit out of this function early. If none of these, what you can consider guard clauses, if none of these guard clauses evaluate, in other words, if none of these return statements exit out of the function, then we set the direction. When it comes to moving, we basically want to start from the first block. So basically the head, let's just unpause and let's maybe travel right, because right I think is easy to work with. We start from the head and then we work backwards. So basically what we want to do is we want to move the first block, and then each of the previous blocks should take the position of the block after it. So if I move the head from here to here, the last block should take the position of this block should take the position of this block should take the position of this block, and this block should take the position of the head previously. So that's basically the approach that I'm taking. So I calculate I store the current position of the first block. I move the first block depending on the direction, and then I've got another loop here that basically does exactly that. So we start from the block after the first block, and we go up until the end of the blocks. Each block is one square, and I move the block after the head, and I store the position of the block after the head. And then when the loop repeats, we take that stored position and we apply that position to the next block, which is kind of what we looked at earlier. So we're using this move block function, and what this is doing is it's creating a new variable, a new coordinate with the position of the current block. So we're remembering the position of the current block. And this is something that might come up. Whenever you need to swap things, you may need a temporary variable like this. So this is a temporary variable that's just storing the current coordinate of the current block. We update the current block, and then we return that temporary variable that we had. And that position of the current block ends up getting used as the position of the next block. When it comes to drawing, again, we're using a loop because we've got many blocks that we need to draw. So we basically start from where are we? So we start at element 0, which is the head, and we draw it, and we basically loop through it until we've drawn all of the blocks. So nothing too crazy happening there. For collision detection, when we're eating an apple, we basically want to just look at the first block. So if, the first block is what's kind of indicating the direction that we're traveling. So the first block is always going to be the block that collides with the apple. or with itself, or with the wall, or anything. So the first block is always the one that we want to examine when it comes to collisions. So we take our first block, we create a new square with it. Technically, we didn't have to do that because it's already a square, but yeah, that's fine. And then we use this did collide function. And did collide is basically saying, okay, you've got a square, you've got a collider. So the collider is the smaller of the two units. Did the collider collide with the square? So in our scenario, the apple is the smaller of the two units, and it's just checking, does the x and the y of the apple, is the x and y of the apple inside the square, basically? If it is, you've got a collision, and then we return true. Where this eating apple is actually used is back in main, so we've got our main loop. If the snake is eating the apple, reset the apple to a new position and call eat on the snake. So when we call eat, we play that eat sound, we increase the length, we add another block to it. The new block is a new square, and we set the position of the new block to be the position of the last block, and then we append it. So at this point, you've actually got an overlapping block. The new block that just got added is at the same position as the last block, but I live with that. I don't really mind it, because as soon as the snake moves, you'll see it grow. So that's all good. I can show you what I mean. If you pay close attention, the moment we eat the apple, it's only really after you start moving that the new block becomes visible. But I think that's fine. Let me pause it again. Oh, there we go. Okay. For calculating out of bounds, out of bounds is easy. We're just checking against 0, and we're checking against the width and height of the surface, and we just need to consider both the x coordinate of the first block and the size of the first block to determine that. But yeah, that's nice and simple. If you're eating yourself, well, before we look at that, let's look at the die function. So if you're out of bounds, which is again controlled in the main game loop, if you're out of bounds, we call snake.die, and snake.die accepts a reason, which we use in this print statement here. We play the die sound and then we reset it, and we've already gone over how that reset happens. If you're eating yourself, this one's perhaps the trickiest part. So we start looking at the first block. As we said, that the head of the snake is the thing that's, whoops. The head of the snake is the thing that's going to collide. Either collide with the apple, collide with the edge of the world, or collide with oh, don't. We're one block too short for that to work. But I think I can do it this way. Yeah, there you go. Anyway. All right, so we can see down here, the reason why we died was a collision with self. That first block is the thing that's going to collide. So we take the first element of the blocks array, store that in first block. When we calculate the collision is based off of one thing being smaller than the other thing, or one thing being inside another thing. So in order to get that to work well, we want to calculate the center of the first block. Because if you think about it, the first block is always touching the second block. There's no gap between the first block and the second block. And you might say, okay, well, you can ignore the second block, but you can do, funky things like this. Where the first block is touching the second block and the fourth block but it's not actually colliding with it, it's just touching with it. So to get this collision detection to work well, I decided to take the center of the first block and compare the center of the first block with any of the other blocks except for the first block. It's important not to compare the center of the first block with the first block, because the center of the first block is, of course, inside the first block. So how do we do that in code? Well, we grab the first block, we calculate the center. So we basically divide the size divided by 2, divide the size divided by 2. And we use this 1 and a colon to indicate that we only want to loop through the blocks from position 1, remembering that arrays start at position 0. So that will basically skip the head. And if the first block did collide with any of the other blocks, in other words, the center is inside any of the other blocks, we return true. And in going back to the main game loop, if that returns true, we kill the snake. And I feel like I've been talking for quite a while, so sorry if that did get dry at some points. But that's basically Snake. Some parts of it are tricky, mainly dealing with like collisions with self and things like that. And again, sorry for any Python veterans who were crying looking at my hacky Python. But yeah, hopefully for anybody that was thinking about making a Snake clone or getting started into coding, I hope that you guys found this somewhat helpful. If you'd like to see a video of something else, maybe going over in a little bit more detail any of the topics that I covered in this video, let me know, and I'll catch you later. See yous.